All right, so inductors in the S domain obviously look a little bit scarier, but really nothing crazy here. Let's break this slide down. First and foremost, we know that the voltage across an inductor in the time domain is equal to L multiplied by the derivative with respect to time of the current through the inductor. If you wanted to solve this differential equation for IL, you can get to this point here where you're integrating the voltage. This is kind of the similar thing to what we already did with the capacitor. This isn't particularly relevant. What is relevant, though, is these two equivalent alternative models for the inductor in the S domain. So the first one, you can get there by invoking the time differentiation property of the Laplace transform. So VL of t, we're saying, is equal to L dIL of t dt. And we know that using time differentiation, we can convert this into the S domain. And we can say VL of S is equal to, it's going to be basically our L, which is going to come along for the ride, the constant, multiplied by, we have to multiply the function by S in the S domain, and then we have to subtract the initial condition for that particular quantity. And so if we multiply through here by L, we get SLIL of S minus L times IL of 0 minus. And that's exactly what we see right here. And so this is a voltage, right? It has to be units of volts here and units of volts here. And so we can model the inductor itself as the current through the inductor multiplied by the impedance of the inductor, right? IL times SL, right? We know V is equal to IZ. So that initial voltage here is the VL times IL term. It's SL times IL, and you can see that. And then to get the full voltage, we have to also add this or subtract this initial condition term, which happens to be the initial current multiplied by L in the S domain. And so that's one model where we model the entire inductor in terms of the voltage across the inductor and the voltage of the initial condition. We can also model it as an inductor in parallel with a current source, and that just basically is directly from resolving this expression for IL of S. So I can take this expression and I can say VL of S, right? I'm going to add this term over to the other side. So I get plus L times IL of 0 minus is equal to SL times IL of S. And so now I could divide both sides by SL. I get VL of S divided by SL plus IL of 0 minus divided by S, and that whole thing is equal to IL of S. Of course, IL of S is a current, so both of these terms should be currents, and that's exactly what we see. So we know that the voltage across this impedance divided by the impedance, VL of S divided by SL, that's going to give me a current here. And then this other term, IL 0 minus divided by S, that gives me a current here. So that's my initial condition term. And this expression here matches exactly what we've got here. And so that is all there is to modeling the inductor. You can use either of these models. They are equivalent models. One may make more sense in one case, one may make more sense in another case, but just so you know what's going on here, all we've done is taken this expression for the voltage current relationship of an inductor in the time domain. We've used time differentiation property of the Laplace transform to convert it to the S domain, that same relationship. And then we've basically derived two different ways to represent this element in the S domain. We can represent it as an inductor in series with a voltage source, or we can represent it as an inductor in parallel with a current source. And this should be obvious because this is just source transformation at work, which we've seen time and time again. Okay, so I'm going to go ahead and end this video, and in the next video we will look at the capacitor in the S domain, which we shouldn't have any surprises there. It's going to be really similar to what we just did with the inductor.